Hey y'all, in this lesson, I'm going to be teaching you about the Z-interval procedure, which is a confidence interval when the population standard deviation is known. I am going to show you how to do this by hand and also using the calculator. As with most things, I really like to show you where things come from before we jump right into just using the calculator and not really thinking about it. So I have taught you about confidence intervals using the empirical rule. And that empirical rule was the 95% was 2 standard deviations, 99.7, that kind of thing. I'm not going to get into it. If you need to watch it, go back. But this is using Z-scores to help us find confidence intervals. And so it may not be a nice, neat, even, 2 standard deviations or 3 standard deviations. It might be 1.6 or 1.7 or whatever. So this is going to help us dive a little bit deeper into confidence intervals. And also keep in mind that this video is for confidence intervals when you know the population standard deviation. When you don't know the population standard deviation, there's a different procedure, which I'll show in the next video. So first, let's draw we have a bell curve. We don't have to draw it. This bell curve is a little bit off. It's supposed to be kind of levitating off the axis, but it's okay. We can use it. And we're trying to shade in an area that represents data that falls within 2 standard deviations of the mean. And we know from the empirical rule that that is 95% of the data. So our mean is here at the center. This would be 1 standard deviation. This would be 2 standard deviations, 3. This is a standard normal curve. And we're wanting to shade 95%, which is 2 standard deviations. And in the last video, we used that to help us form these confidence intervals. So how much of the bell curve is shaded? Well, I already kind of told you 95%, which is 0.95. And that's here. Then we're going to call the unshaded regions alpha. And if I were to split alpha up into 2 tails, because if you remember from one of my previous videos, we had Z sub alpha, and that alpha represented a right tail. But in this case, we don't just have a right tail, we have 2 tails. So that means I'm going to be splitting alpha up into 2 pieces. Now, if we just think about 95%, how much is left over that's not shaded? 5% is not shaded. But since we're talking about a confidence interval, we have 2 tails at the ends. So that's going to be 5% split into 2, which is 0.05 over 2, and that's going to be 0.025. So each tail is 0.025. And that represents alpha over 2. So when we are talking about confidence intervals, we end up with these 2 tails, and that's really going to come into play again when we talk about hypothesis testing, whether it's right-tailed, left-tailed, two-tailed. We won't get into that today, but we will later. For this and other confidence levels, we use alpha, where alpha is 1 minus the level of confidence in decimal form. So for example, when I use 95%, that was 0.95. That would be a confidence level. And so it's a problem, with 95% confidence, we can say that the population, blah, 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 we'll get into it later, but that's your confidence level. And alpha is 1 minus your confidence level. So that's how we found 5%. 1 minus the confidence level in decimal form split into 2. So that's just kind of getting you oriented to some of the language and kind of a picture of what that looks like. Recall that a Z-score indicates the number of what? Standard deviations a given value is from the mean. And Z sub alpha represents the Z-score that has an area alpha to its right under the standard normal curve, which means that Z sub alpha over 2 is the Z-score with an area of alpha over 2 to the right. Draw a bell curve to show all of these things. So if you can, pause the video, draw this out on your paper, and come back and check it. So you should have something like this drawn. I did not ask you to do 1 minus alpha, but just to kind of give you the full picture, I wanted to put that in there. Alpha is the two pieces on the tails added together. And so each tail is alpha over 2. And then if we were to add those together, that gives us alpha, which means that this shaded region in here, wherever you shaded, it doesn't matter, is 1 minus alpha. You could have done 1 standard deviation. It doesn't matter. It just did some shading. And then your population mean is at the center with these as your standard deviations. So that's just kind of a general picture of what we're looking at. And it always helps as you're working through these problems to either envision that picture or just go ahead and draw it. I usually just go ahead and draw it because it helps me make sense of what I'm doing. To calculate a confidence interval based on a certain level of confidence and the population standard deviation being known, these conditions must be met. The sample is random, the population is normally distributed, or the sample is large, and the population standard deviation is known. So if these 3 things are not met, or 4 kind of, 3.5 are not met, then you can't really do a confidence interval based on a confidence level. We can use a table to find the Z-score associated with alpha or the confidence level, vice versa. And to find a confidence interval to estimate a population mean, we can use this formula. So what's happening here, I'm saying a lot. I'm not saying a lot, but I'm insinuating a lot. We are using a confidence interval to help us estimate what we think the true population mean is. So maybe we don't know the population mean. Obviously we don't, because it says these 3 conditions must be met. It never says anything about the population mean. And the reason why it doesn't is because we're using confidence intervals to help us narrow that down. And what's happening is based on a certain level of confidence, we'll have a Z-score, and we can say within this range, we're 95% confident or 90% confident or whatever your confidence level is, we're pretty sure that the population mean is within this range. And that range comes from your confidence level, which gives us alpha, which gives us Z, which gives us the number of standard deviations, which gives us this range. So it's all tied together. I love this chapter. I love this part of the textbook or statistics because it really brings in everything we've learned and puts it all into one chapter, just in this beautiful thing. I love statistics. So we have a formula I'm going to show you in just a second. So the formula for this, what we don't know is the population mean, but what you do know is a sample mean. And what's happening is we're trying to estimate the population mean based on the sample mean. So we have a sample mean and we have a Z-score, which is like a standard deviation. It's the number of standard deviations from the mean. And then we also have the standard deviation of the sample mean. So this is going to be this is a sampling distribution, and it ties into the central limit there, all the things apply. Oops, I made a mistake. That's only one side. I said it was a range, an interval. A confidence interval. An interval, if you remember from algebra, is like a range of values. And intervals are denoted by either parentheses or brackets. In this case, we're going to be using parentheses. But it's got like a parentheses, a number, comma, a number, parentheses. Number, comma, number, parentheses. And this is an interval, and it's a sentence saying that it's a range of values between these 2 numbers. So we call this one the Z-interval procedure, which I mentioned at the beginning of the video. And it might make sense that it's Z-interval because we're using Z-scores because we know the population standard deviation. So when you don't know the population standard deviation, we're going to be using a different interval procedure. So it does matter, and you do have to pay attention to that. When can we use the Z-interval procedure? Like I said earlier, this kind of ties into the central limit theorem. You're going to see some overlap here. If your sample size is small, which is less than 15, the Z-interval procedure should only be used if the population is, if y'all remember from central limit theorem, normal or normally distributed. If the sample size is medium, that's between 16 and 29, the Z-interval procedure is okay to use if there are no outliers and the variable under consideration is normally distributed. And then if it's a large sample size, 30 or more, then the Z-interval procedure can be used without any restrictions. It doesn't have to be normal or anything like that. So it's kind of a nice review of central limit theorem. Which part of the confidence interval is considered the margin of error? So I mentioned that the confidence interval is giving us this range of values where we think the population mean will be. And I wrote out this thing. It was just like a little fake interval. And these two numbers represent boundaries, kind of the endpoints. And those endpoints are X bar minus this little piece here, comma, X bar plus this little piece here. So the formula gives us our two endpoints, and our population mean is supposed to be in the center. And the margin of error is kind of this fluff or buffer, kind of. It's a buffer to say, oh, we're 95% confident that it's within this region. It kind of gives us this comfort zone of where we think it is. And so the piece that's the margin of error, I'm sorry, I wrote that wrong. That's X bar. X bar is in the center. Very sorry. The piece that's giving us this fluff is here. We're going to go minus that amount, and we're going to go plus that amount to give us that buffer. I forgot a parentheses too. Usually I have students in front of me that can tell me, you forgot something. Okay. So the center, the anchor point is the sample mean. And then the buffer is the margin of error. And so we have the sample mean, and then we have this margin of error that's giving us this kind of cushion. And that margin of error is the highlighted piece. So margin of error is that plus or minus Z sub alpha over 2 times standard deviation. And then the center, which kind of makes sense if you think about it, is the sample mean, which is a measure of center. So it makes sense that it's the center. Get it? Okay. And I could probably draw that out if you're having trouble with the wording here. I want to draw this out on a number line so you can kind of see what's happening here. We've got X bar in the center because mean is a measure of center. And then we have this interval that's made by adding that margin of error and subtracting that margin of error. And that gives us those in pieces. And I'll show you some examples. Don't worry. If you don't get it, don't worry. I'll show you some examples. You know I will. We have some really common confidence levels that we use over and over and over again. And we did see in the previous video doing confidence intervals using the empirical rule that when we looked at 95%, we just called that 2 standard deviations, and we just used 2 for our z-score. But it does have a more exact number. So as you're working through problems, just make sure what they're wanting you to use. If they say to use the empirical rule, then you can do the 1, 2, 3. But if they don't, then you want to find that more exact number associated with the confidence level. So also remember the picture that I drew with the shaded region. So for a confidence level of 90%, that means 90% is kind of here in the middle, and then it has these 2 pieces on the end. If it's 90%, then that leaves 10% left over, which leaves 5%. I'm going to put it in decimal form for each piece because we're splitting it in 2. And then the z-score associated with 0.05. Now I've got the negative side of the z table here. We're just going to kind of ignore the negative part. It's okay. It's just representing the left side instead of the right side, but they're symmetric, so it's fine. But this is the negative side of the z table. We're going to locate an area of 0.05, which is, I'm going to use my highlighter, about here. Oh, that's a little big. Let's start over. It's like in between here, which is about 1.645 if I were to estimate. You can also use, if you remember, inverse norm of the area. And we can do that just to review it. Second vars, inverse norm, area of 0.05, mean of 0, standard deviation 1. And there's that negative 1.645. It did come out negative because it's giving me the area to the left. So it's giving me the left tail. If I wanted the right, I would have to, it's a different story. Don't worry about it. I can show you, but I don't want to waste your time. So 95% leaves 5% for alpha and 0.025 for the tail. So we locate 0.025. I want you to pause it, try it, and fill in the table, actually. If you filled out the rest of the table, it should look something like this. This table, I put this in here because I mentioned these are commonly used confidence levels. So if it's something that you want to reference back to, or even just something that you want to make sure you fully understand because you're going to be using it over and over again, that's a good idea. And if it helps, remember that you can draw that normal curve, shade in that region that we're looking for, and that might help you kind of have a more concrete understanding of what we're looking for. So what we're finding is the z-score associated with that shaded region. So if I were to shade, I'm just going to draw a real bad picture here. I can't even handle that. If I were to shade 90%, then the z-scores associated with that would be negative 1.645 and positive 1.645. And that's going to give those little tails on the end. And I mentioned the reason why it came up negative is because I did this area. So if you wanted to find the right side, it's symmetric, it's positive, or you can find this area. But anyway, moving on. We have an example. We have the sample mean, the sample size, and the population standard deviation. This indicates right here, we're going to be using the Z interval. And then we have a confidence level of 95%. So what we need to do first is find the Z-score associated with that confidence level. And I just did it in the table, so I'm going to not cheat, but use my resources here. I just did it, so I don't want to recreate the wheel, reinvent the wheel. The Z-score associated with 95% is about 1.96. And then the formula for this confidence interval is X bar plus or minus that Z-score times the standard deviation. And then I'm going to plug in my pieces. It gave us X bar. We have the z-score. And the standard deviation comes from the population standard deviation over square root n. I'm going to rewrite this just to simplify it. That's 3/6. And then this is going to give me my endpoints. And you may not recognize this symbol. This is plus or minus. That represents two different numbers. One number is 20 minus this stuff, and one number is 20 plus this stuff. So we're going to type both of those in separately to figure out those two endpoints. And that will give us our interval. So I'm going to pull up my calculator. I've got 20. I'm going to start with the smaller one. So I'm going to start with minus 1.96 times, I wrote that wrong. Dadgummit. I'm really sorry. That's 0.5, 3/6. And we get 19.02 for the left bound. Then I'm going to go second entry, change this to a plus. And that gives me my right bound. And it wants to know next what the margin of error is. Well, what I have is this interval, which provides these endpoints. And what I know is that the center is 20. So if you can envision a number line here, we've got 20 in the center. And then we have 19.02 and 20.98. So how much change, how much buffer exists right there between the center and the endpoint? That is 0.98. And then spoiler alert, if you type just this in, let's do it. You know we have to do it. 1.96 times 0.5, 0.98, which is what I was showing you earlier, that little piece is your margin of error. It's giving you that space in between the mean and the endpoint. Isn't that so pretty? Isn't it so nice? I just love this. I think it's so cool. I hope you do too. And then we're going to interpret. Last part of this problem, we're going to interpret. We can be 95% confident that the mean, the population mean, or they say the mean of all subjects, which means the population mean, in this study, we're between 19.02 and 20.98. And that's all. That's all you have to do. It literally gives you everything you need in this piece here, except for the z-score and the adjusted standard deviation. That's all. So simple. So now that you know where it comes from and how it's built, I'm going to show you how to do it on the calculator because it's faster. I have up here the steps that you're going to go to. You're going to go to Stat, Tests. You're going to select Z interval, and I'll show you in a second. Z interval. We're going to put in stats, not data. Now, if you do have data, like if you have a data set, then you can put in data instead. But in this case, we were given stats. And then input your info, hit enter. There you go. So let me show you this first one. And then I'm going to let you fill out the rest on your own and come back. So in the first one, we're given the sample mean, the sample size, the standard deviation, the confidence level, and we have everything we need to input stuff into the calculator. So we're going to go to Stat. We're going to go over to Tests. Mine's at the top. You can see you're going to have to go over to Tests. This is a Z interval. It's an interval because it's a confidence interval, and it is Z because we know the population standard deviation. Then down at the bottom, it's wanting us to input our statistics. And remember, statistics are just numbers. If you don't have these numbers, then you can input data instead, but we have the statistics. So the population standard deviation is 3. The sample mean is 20. Sample size is 36. Confidence level is 90. Enter. Mine has it right there on the right. Isn't that so nice? That was really fast. I love it. So my confidence interval, I'm gonna have to write small here, is 19.17 to 20.82. And then to interpret it, we're gonna say we are 90% confident that the population mean lies between 19.17 and 20.82. So that's all. That's all you have to do. I want you to use your calculator. You can do it by hand if you want to, but I want you to practice one or the other. Fill out the rest of this table and then come back. If you're doing notes on like an iPad or a tablet, I want to show you a trick here. If you're using GoodNotes, I'm going to lasso this. I really don't want to rewrite this over and over again. I'm going to copy. I'm going to go down here, hold it, paste. And then I'm just going to change the pieces that I need to change. So if you're using a similar device, you might try that. All right, so hopefully you finished your intervals. Go ahead and check your numbers with mine. Just make sure they're the same. And then your interpretations, they're pretty much the same interpretation over and over again. But the point of this is what I want you to notice from the intervals. You might be wondering, why did we do so many? But you might have noticed as you were inputting these statistics, what changed. So in the first 3 examples, everything stayed the same except the confidence level. And then in the next 3 examples, the confidence levels were changing, but our sample size was larger than in the first 3. So we're going to use that to kind of make some comparisons between the intervals. Let's first talk about the confidence level. So when the confidence level changed, let's just look at the first 3. Everything's the same except for the confidence level. And it might help as you think about this to envision a number line. So in the first example, we have 90% confidence, and that put us at 19.1 to 20.8. And then when we went to 95, our confidence level expanded a little bit. And then when we went to 99, it expanded even more. So a larger confidence level casts a wider net. So it kind of gives you a little more safety. Let's summarize that here. A larger confidence level casts a wider net for the confidence interval. Now let's look at the sample sizes. So let's just, for the first one, let's compare this one and this one. They both have 90%. Everything else is the same except for the sample size. So what happened to the confidence interval when the sample size got larger? Draw some conclusions, pause it, draw some conclusions, come back. Hopefully you saw that it got narrower. So we were able to narrow down our confidence interval when we had a larger sample size. So the larger the sample size, the closer we are to narrowing down that true population mean. So as n gets larger, the confidence interval gets narrower. We're zeroing in on or getting closer to approximating or estimating the population mean. So let's use that. and work through this example. Write out the formula, just a summary, write out the formula for finding a confidence interval by hand. I want you to go ahead and actually, I'm going to zoom out. This is just kind of like a summary of the lesson and tying it all together. I'm going to zoom out. I'm going to let you fill out this table and this question, come back and check your answers. You might have some slightly different answers depending on how your brain thinks for these, but you should be pretty close. The formula just came from a previous page in the notes, so you just rewrite that down, and hopefully that's helping you narrow down what's missing in these examples. So in the first example, we have a list of data, the population standard deviation, and the confidence level. So the confidence level is going to give you Z. What we need is we need to count up the number of items in the list of data for N, and then we need to find the sample mean based on the data. So you may be asked to do something like this in your homework. You might be given just this information, and with that information, you have to be able to build that. And so you have to know what's missing. In the next one, we have the sample mean, and we have the population standard deviation. So what we're missing is a confidence level or a Z-score, and we also need N to be able to find this piece. In the next one, if we have the margin of error, then technically all we need to build an interval is the sample mean. And then the last one, if we have the confidence level and we have the sample mean, then what we're missing is the population standard deviation and N. That's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know and I'd be happy to help. See you in the next one.